Welcome, viewers. Today we want to look at a practical example of a design of a composite section. So we are going to look at this exercise. The question is, it goes thus. In a grid analysis of a 15-meter span simply supported bridge deck consisting of 7 beams at 1.65 meter centers, the bending moment on the penultimate beam taken from computer printed as shown in table 3.3. Now let's take a look at table 3.3. Bending moment for beams in example 3.1. We are going to look at the life load moment ML, which comprises of HB load plus 1/3 HA and the footway load in kilonewton meters. We also have the load. We also have the load that is due to the self weight of the precast section in kilonewton meters. We have the various load at various positions. Last on the column, we have the load due to in situ slab. We'll have that on that column. Now, if you look at the loads, they are the value for the moment at various positions along the beam: 0.1 L, 0.3 L, and 0.4 L, as well as 0.5 L has been taken on the table. Other parameters, including the sectional modulus with respect to fiber 1 and 2, Z1 and Z2, with respect to the precast section, as well as Z1 and Z2 prime sectional modulus with respect to the composite sections are also available in the question. Take note that the neutral axis of the beam from the soffit is 0.408 meters. So now we are going to plot the cable zone as well as drawing the cable profile. So we are going to be doing this. We have it in parts. So if you are new to this channel, please do well to subscribe as we take them from part to part. All right. All right, so we are going to work on that. We have a Z1 plus Z2 over A. We'll need to work out these parameters as we're going to make use of them in our formulas. We'll have that with 0.3654 meters. Z1 over Z1 prime, we have it to be 0.5733. All right, Z1 prime over Z1, which is the inverse, we have it to be 1.7442.8. All right, Z2 over Z2 prime, we have it to be 0.17436. The inverse of it, which is Z2 prime over Z2, we have it to be 5.73506. Okay, now the next thing we want to do is to check whether our choosing section for this design, the sectional modulus is greater than the expression we have on the board. We have Z1, which is our choosing sectional modulus to see if it's going to be greater than the value gotten from the expression. So we'll have it as Z1 is greater or equal to MdB plus ML, Z1 over Z1 prime, open and close bracket. Okay, so that is what we have. So if we work that out, remember that we are going to take the mid section, which is 0.5 L, which is the mid section of the beam. At that mid section, we'll have the moment due to the self weight of the precast of the in situ section, to be 178 kilonewton meters. So we'll have that MdB. And the moment due to life load, which is a HB load, 1/3 HA, and footway life load, we have those values combined to be 1,220 kilonewton meter. So we're going to substitute them into the expression Z1. So if we substitute them into the expression Z1, we'll have that Z1 should be greater than 0.0421251 meter cube. Okay, so let's check out for that. Remember that our Z1 is 0.059, and here we have our Z1 to be greater than 0.042, which is true. So if that is true, it means that is okay. All right, now we're going to check out for Z2. To check out for Z2, you discover that our MdB remains 178. Our life load ML remains 1,220. So substituting the value as it were, we are going to have our sectional modulus with respect to fiber 2 to be greater than 0.0 212.075 cubic meter. So let's check to see if that is true for the section. Remember from what we saw, our Z2 for this particular precast section is 0.04786. So that value is greater than 0.0212.075. So we can say that this is true, and therefore the section is okay. All right, so we've been able to check the adequacy of this section, and we can say that the section is okay for the design. But the next step we are going to take is to determine the required pre-stressing force for this particular precast section. Okay, now we have derived the upper bound limit of pre-stressing force in our previous videos, and the lower bound limit, remember P8 is the notation. We'll say that the upper bound limit of the pre-stressing force is the maximum fiber stress Z1 plus Z2 minus NDB minus ML open bracket Z2 over Z2 prime close bracket. Okay, so this is the expression for the upper bound limit of pre-stressing force. So when we work that out, we're going to have the upper bound limit of the pre-stressing force, P8, to be 5040.92 kilonewton millinewton. Okay, so this is the upper bound limit. So we're going to determine the lower bound limit so we can select the appropriate pre-stressing force. Look at the lower bound limit of the pre-stressing force. We have it as P9, and we have P9 to be greater than the expression we have 178 times 10 raised to power 3 plus 1220 times 10 raised to power 3. If we work out that expression carefully, we are going to have the lower bound limit of the pre-stressing force to be 2400.98 kilonewton. Now, having gotten the lower bound limit of the pre-stressing force, we are going to choose a pre-stressing force between the range of 2,400 to 5,040 kilonewton as our upper and lower bound limit of pre-stressing forces. And we're going to pick a pre-stress force within this range. We have that to be P, between P10 and P9. Of course, P10 is the economic limit for pre-stressing force. And for us to choose equation P10, of course, we know that equation 6 is the criteria for equation P10, okay? So from our derivation of the formula, if we go back to the equations, for those of us who are new to these expressions, you go back to the derivation of this equation, we're going to see where we obtain P10. Now, your value for P10, which is the economic limit, will be checked if P10 is the right equation for the economic limit. Now, for us to check that, you can see we have P10 to be 3,382.18 kilonewton. We are choosing a pre-stressing force P to be equal to 2,500 kilonewton. That is our choosing pre-stressing force. And we want our P should be economical for the design. So P should be between P9 and P10, okay? But just to be sure that our P10 is the right equation for the economic limit, we are still going to check that. And for us to make use of P10 as the right equation for economic limit, we will check that our MDB, open bracket Z1 prime over Z1 minus Z2 prime over Z2 must be greater than Z1 prime minus Z2 prime, F maximum minus F minimum. If this condition is okay and is so, our equation 10 choosing as the economic limit of pre-stressing force is okay for us. All right, so from the expression, from the design, you can see that equation 10 is the right equation to choose for the economic limit of pre-stressing force, and that translates to 3,382.18 kilonewton as the limit. Okay, now having gotten this, we are sure of the pre-stressing force. Of course, we need to check for the cover requirement for this pre-stress. So if we must check for the cover requirement, we know that the minimum 50 mm, we have the cable duct diameter to be 71 mm. And we can as well check these values from the table 36 of BS 500 1990 part 4. Radius of curvature 40, minimum cover 50 mm. We can check that. The center to center spacing of a duct should be, the minimum distance should be 142 mm. All right. So if you look at the body, you see I've redrawn the composite section, and we see that the minimum center to center spacing between the duct, let's assume we're using two tendons. We are going to have 142 millimeter center to center. Now, having gotten all these values, let's look at the losses. Of course, there are losses that are usually encountered in the design process, and these losses are practical. We have losses that are due to shrinkage of concrete. We have losses that are due to creep. We have losses that are due to friction between tendons and concrete. We have losses that are due to relaxation of the strands and the tendons. All these losses are going to play a key role in the actual value for the pre-stressing force. So if we are going to be experiencing losses of about 25% of the pre-stressing force, it means if we are choosing a pre-stressing force of 2,500 kilonewton, it's not going to be adequate because we are going to lose some pre-stress force along the profile of the tendon. So for us to avoid a situation by our pre-stressing force does not satisfy the necessary fiber stress criteria, we are going to increase our choosing pre-stressing force so that by the time we are losing 25% of the choosing pre-stress force, our force will still remain at 2,500 kilonewton. Okay, so that is exactly what we're going to do. So if we do that, we're going to have the new force to be 2,500 divided by 0.75. And if we do that, we're going to have 3,333.3 kilonewton as the new force. So if you take 25%, if you lose 25% of that particular force, you will have it back to be 2,500 kilonewton. All right. So we're going to be working with a pre-stressing force of 3,333.3 kilonewton as our pre-stressing force. Okay. All right, so we are going to look at how we can choose pre-stressing cables from pre-stress concrete design manual. You can look at the manufacturing manual to pick various sizes of pre-stressing cables for the required pre-stressing force. So we are going to look at the K-range system of Fresnet pre-stress manufacturing company. And under that, we have, if we're picking a cable from a grade, steel grade of 1,800 megapascal, that is the steel grade of the pre-stressing cable we are going to choose from. And if we look at using the European norm, from the European norm, we can look at 138 to 169/79. From that European norm, you will see that for a pre-stressing cable of 12 strands, cable diameter of 13 mm, we are going to have the ultimate tensile strength of that cable at 100% to be 2,076 kilonewton. So that is the ultimate tensile stress. So this ultimate tensile stress for this cable at 100% is this. Of course, we won't like to stress the cable to 100%, of course. So normally you take 80% of the cable. The cable should be stretched or stressed to about 80% of its total tensile stress. So if you take 80% of the total tensile stress for this particular cable, you're going to have it as a 1661 kilonewton as the value of the tensile strength. Okay, so if the tensile strength stress of the ultimate tensile strength of this cable at 80% is 1661 kilonewton, which we are going to make use of because our cable, which we intend to stress, should not be stretched beyond 80%. So whatever force we are applying to the cable, we limit it to 80% of its allowable tensile strength. Okay, so based on that, we have our total choosing pre-stressing force having added losses to it to be 3,333.3 kilonewtons. So we're going to divide it by the number of the value for 80% tensile stress. So for do that, we're going to have our number of cables to be 2. So we have 2 cables with just 2 points of fractions. But we are not going to, we're going to look at it for us to be more, be in a more safer position. Instead of taking 12K13, we can, if we check the table, we can see that from the European norm table, we have the next after 12K13 to be 19K13. And if that cable still, the grade of that cable remains the same, 1860 megapascal. The ultimate tensile strength of 19 is 3287. And that for 80% of this tensile strength, we have 2,630 kilonewton. So this is the tensile strength we're going to have. So if we divide this by the ultimate tensile stress to know the number of cable for 80%, we'll have 1.26 numbers of cables. All right. So from all implication, it's obvious we are going to make do with 2 cables of 19K13. Okay. So the number of cables that will be required for this section is 2 19K13 cables with ultimate tensile strength at 80% to be 2,630 kilonewton for the cable. So, okay, so once we have gotten this, we know the number of cables that we need for this particular design. The next thing we will do is, like we said earlier, we still need to check the cover requirement for this cable to be sure that our choosing pre-stress force meets with the cover requirement. So let's do that of the cover requirement. We have the KE1, which is K with respect to fiber 1. So we'll look at KE1. All right, so from the question, we'll have our KE1. Our KE1 becomes the centroid of the precast section minus the cover minus half the diameter of the duct. We have a 71 diameter duct, so we work that out, and if we do that, we have our centroid from the bottom fiber 1 to be 0.408, so we work that, we'll have KE1 to be 0.3225 meters. All right, now in determining the equation of the cover requirement, remember that the choosing pre-stress force must be greater than the expression, which is this expression. So we'll call it P13. We'll call it P13. So that choosing pre-stress force must be greater than this expression. Similarly, also the choosing pre-stress force must be greater than this expression. We'll call it P14. Okay, so our choosing P should be greater than this expression. So let's substitute values for this expression. If we do, here is 0, so work that out. We're going to have 2049.207 kilonewton here. And we have P14 to be greater than this. If we work out P14, we're going to have P14 to be negative 408.509 kilonewton. All right. Now you can see that our choosing pre-stress force is greater than P13. Of course, P13 is higher than P14. So if our choosing pre-stress force is greater than P13, what it means is that we'll say that the cover requirement has been satisfied in this scenario. All right. So now we've been able to check the cover requirement. We've determined the numbers of cables, and we can proceed further in the next part of this video. So for those of us who are joining us for the very first time, we're going to continue this class in parts. I want you to stay tuned. Hope to see you in our next class. Do well to enjoy yourself and have a wonderful day. My name remains Engineer Baga. Have a lovely day. Thank you.